Australian domestic renewable energy market, photovoltaic systems or PV are a standout success. From 2009 to 2011, installed PV capacity grew tenfold, and today around 1 in 10 Australian homes have PV arrays. Although most feed-in tariffs have now wound down, demand for photovoltaic power shows little sign of abating, with PV systems already installed in more than 1 million homes. While photovoltaic is now the clear leader in domestic and small-scale renewable energy generation, other technologies such as fuel cells and small wind turbines may shortly make their presence felt. That means sooner or later emergency service crews will find themselves working to save lives and property in premises equipped with some type of alternative electrical generation. A possibility that should now be included in the risk assessment of any emergency incident. Nonetheless, with the large number of photovoltaic systems installed, the priority for emergency crews is to know how to recognise and work safely with and around PV installations. Typically, a domestic PV array is roof mounted, and as the most obvious indication of its presence, its panels may be visible from the street. But even with a 360-degree size up and a dynamic risk assessment, the panels of some installations, particularly those on flat roofs, may not be seen from the ground. So if a building is unoccupied, emergency personnel need other ways of quickly checking for the presence of a PV system. Most urban PV installations are grid connected, requiring an inverter to convert the direct or DC current collected by the solar panels into the alternating or AC current required by a home's electrical system and appliances. Even for relatively small PV systems, the inverter is an easily recognised device with a display panel and LEDs that monitor its operation and performance. In most houses, they will be attached to an outside wall, often in proximity to an externally located switchboard. In some cases though, both the switchboard and inverter may be located inside. Gaining access and finding the inverter will take time, but if there's an external electricity meter, the labelling required in a number of states may provide another avenue to quickly confirm the presence of a PV installation. There may also be labelling at the point at which the power from the grid connects to the house. However, where lack of any external signage or physical indication necessitates an internal inspection, labelling on the switchboard should provide a quick confirmation of a PV installation. This is nationally mandated by the Australian Standard 5033, but the label may not always be present, for example if the system was installed prior to the Australian standard coming into force. As we've seen in urban locations supplied by the mains power grid, most PV systems will be grid connected, supplementing but not replacing the electrical supply from the grid. However, in remote and rural locations not connected to the mains grid, standalone PV systems can be used to generate all the electricity required for domestic uses. Of course, with limited solar radiation available when the sun is obscured, and none at all at night, standalone PV installations need batteries to store and release a continuous electrical supply. Typically arranged in series to boost their voltage, these batteries are, in absence of any other form of electrical generation, a clear pointer in the presence of a standalone PV array. As with the grid-connected system, domestic standalone PV installations also require a DC to AC inverter. This will be found between their DC storage batteries and the AC household services and appliances that the inverter supplies. However, since some items of equipment and household appliances can run on direct current, not all standalone PV systems need inverters. But what they do all need is a charge controller that reduces the variable voltage the PV panels produce to the nominally 12-volt capacity of the batteries. And while considerably smaller than a typical inverter, charge controllers feature similar monitoring panels and/or LED displays. While standalone and grid-connected PV systems are rarely found together, some households or businesses may, for particular purposes, have installed both. Also available are more sophisticated charge controllers that can, when standalone system batteries are running low, direct mains grid power to top them up. These combined charge controllers incorporating rectifiers to convert the AC grid current into DC current for battery storage tend to be larger and more complex in appearance than the simple standalone models. For emergency services personnel working in any damaged premises, the presence of live electrical circuitry can present a very real and immediate threat of injury or even death from electrocution. With buildings connected only to grid power, switching off their AC supply should provide reasonable assurance this danger has been eliminated. Standard operating procedures for doing this may vary from state to state, but even when these have been completed, caution should be exercised in case any unauthorised circuits bypass the switchboard. But to fully isolate a grid-connected or standalone PV installation is a more complex and involved operation. And that's largely because the DC generating PV array itself simply can't be switched off. In fact, even when shaded or damaged, PV panels can continue to generate a potentially lethal voltage. At night too, tests have shown that floodlights or firelight shining directly on PV arrays can generate dangerous voltages, so under all circumstances they must be treated with caution. If emergency personnel are working at night, they should be acutely aware that from daybreak onwards, the array once again generates electricity. With this in mind, relief crews and investigative personnel attending an ongoing incident at night should ensure they're fully informed of any damage to a PV array that might cause live electrical hazards at daybreak. For their part, incident controllers' dynamic risk assessments need to discontinue any daylight work on roofs where damaged PV arrays or DC cables could possibly divert dangerous voltages through the roof itself or any of its fittings. Emergency crews should only resume work when and if a qualified electrician has declared the roof safe. As well as the danger of electrocution, damaged PV arrays create a number of contingent risks. For example, they may break loose from their mountings and either slide down an inclined roof and fall to the ground, or collapse and fall through a damaged roof, potentially injuring emergency personnel working below. Although dynamic risk assessments are designed to minimise all these hazards, buildings equipped with PV systems still pose a heightened threat to the safety of emergency service personnel. For that reason, their natural inclination to save property and even lives has to be tempered by a more comprehensive and focused consideration of the dangers to their own safety that may be involved. For example, if an unconscious but possibly alive individual or group were found on a roof housing a damaged PV array, their bodies could be conducting an unseen but potentially lethal voltage. Under these circumstances, rather than immediately attempting a rescue, the electrical risk must be managed before operations can proceed. As always, the safety of the emergency service worker is our number one priority. Therefore, the system should be treated as live until a qualified person has declared it safe. For emergency service personnel, compounding a potential loss of life by unnecessarily endangering their own makes little sense. So, resisting the temptation to take immediate action in these and similar situations involving electricity is always the most effective strategy for saving lives. Where the risk assessment of an incident reveals the PV array is undamaged, emergency crews should take all care to ensure it stays that way. PV panels are not designed to bear loads, so walking or placing equipment on them should be strictly avoided. By the same token, shifting, removing or damaging panels to ventilate or reach the seat of a fire, or for any other purpose, places personnel at extreme risk of electrocution and should never be attempted. Although standard operating procedures vary from state to state, turning off all AC power to damaged premises is generally accepted as the necessary first step in shutting down the PV system.
Power off!
Main AC fuses and circuit breakers will usually be found on readily locatable exterior or interior switchboards, so switching off AC power before or immediately after entering a house should be a simple operation that reasonably assures the removal of all AC power to its interior circuits. And since PV systems inverters also operate on AC power, turning that power off automatically turns the inverter off as well. In most cases, inverters will also be equipped with their own AC isolators, which should be switched off after their AC power has been disconnected at the switchboard. While switching off the AC power removes the danger of AC electrocution for emergency service personnel working inside that building, the PV array continues to generate and supply DC voltage to the inverter. And though the DC cable carrying that voltage is often routed on outside walls, it sometimes follows a path through the roof and inside the building on its way to the inverter. Unfortunately, the AC detection devices issued to emergency service personnel don't respond to DC current. So under these circumstances, isolating the PV array and its DC cable becomes a priority. A typical shutdown procedure would look like this. First, turn off the AC main switch. Then the solar supply main switch at the switchboard. Second, operate the AC shut-off switch next to the inverter. Third, operate the DC shut-off switch, which is also next to the inverter. If there's a DC isolation switch next to the PV panels, turn this off last. Because PV arrays will only stop generating dangerous electrical voltages when they're totally deprived of light, working around them during daylight hours always involves a degree of risk. The one and only exception is when the array is covered with a 100% opaque sheeting. Anything less, such as a salvage tarpaulin, may admit enough light for the panels to continue generating dangerous voltages. Of course, applying the correct material is a specialised task that should only be attempted when sanctioned by the emergency agency involved and completed by trained and fully equipped personnel accustomed to working at heights. Regardless of whether it is appropriate to attempt to cover PV panels, ensuring optimum safety for emergency service personnel requires the DC isolation switch or switches included in all PV systems to be located and switched off. Some PV arrays will have an associated rooftop DC isolation switch that should be approached and turned off only if the array and its DC cable are undamaged. More conveniently and safely located is the DC isolator Australian Standard 5033 requires, adjacent to the inverters of both grid-connected and standalone systems. It should, however, be remembered that any wiring between the PV panels and the DC isolation switch remain live, even after the isolation switch is turned off. Since most grid-connected systems have inverters attached to an outside wall, locating them should be a straightforward process. However, internally positioned inverters and their DC isolation switches will of course make it necessary to enter the building to isolate the DC power flowing from the PV array. In this context, it's worth noting that as well as DC isolators adjacent to the inverters, standalone systems supplying AC power will usually have an initial DC cut-off device between their PV array and the battery bank. This may be a circuit breaker or fuse that makes it possible for emergency personnel to isolate the battery bank as well as the inverter from the DC power. While batteries damaged by fire, flood or falling debris, whether isolated or not, can emit dangerous fumes and acids. Any leaking liquid is less likely to be electrically charged if the system's batteries have been isolated from the DC current. Even if it has been possible to shut down a building's PV system before tackling a fire in or adjacent to its array, the fact that the array remains live calls for extinguishing media suitable for use with electrical fires. In these circumstances, the preferred choice might be a handheld dry powder or CO2 extinguisher if access to the panels can be made safely, for example on a flat roof. But where an array is damaged or for other reasons can only be reached from a distance, fresh water with or without Class A foam can be used as a broken spray from a distance of at least 6 metres. However, because it's electrically conductive, using salt water should always be avoided. With the fire extinguished, it's important to remember that if DC arcing has caused the fire, or if the fire itself has resulted in arcing, this will continue until the PV panels have stopped generating electricity. The assistance of a solar qualified electrician will be required. Also, all objects in contact with that voltage may remain live and potentially lethal until it has been isolated. This video has dealt with small and household PV systems. However, emergency service personnel may find themselves dealing with incidents at larger commercial premises with multiple PV arrays and components. Essentially, these will operate in the same way as smaller systems, but because of their increased size and complexity, assessing the risks entailed in switching off power to commercial premises will always require expert technical advice, consultation with building management, and more extensive incident control. Finally, although national and state regulations and best practice layouts of PV installations have been detailed here, it should be remembered that older or improperly installed systems may not conform to these standards. With that in mind, constant vigilance and anticipation of the unexpected will always be crucial in ensuring the safety of emergency service personnel.